Thanks for coming to Boston Kai tonight. We all really appreciate it. I hope you find this talk really interesting. I'm sure that I will. We'd like to thank our sponsor, FutureWay. Without them, we couldn't put events like this on. So thank you all for coming, and thank you, FutureWay, for your sponsorship. So the Miro networking event tonight was sponsored by the Co8 group. So thank you very much. I'd like to introduce Daniel Leithinger. We're going to find out what shape displays are and how they enable remote togetherness.
Thank you, everybody, for having me, and I'm really impressed by the turnout here. No pressure. So I'm Daniel Leithinger. I used to live and study in Cambridge from 2008 to 2018 or 2017. And so it's very close to my heart. I'm very, very glad to come back virtually to speak. And for most of the time there, I was a student at the MIT Media Lab in Professor Hiroshi Ishii's group working on shape displays. And did a couple of experiments on how we could use those for remote collaboration. And so when Boston Kai reached out and said, do you want to chat about anything? I was like, I really want to revisit some of these themes and also talk about what we're currently doing to kind of make that happen, because it's just such a pressing issue on everybody's heart. Please see this talk more as a sketch and as a conversation piece rather than a formal technical talk. But if you have any technical questions, because I'm going to mostly play videos, just jump in and ask. I'm either going to answer them at the end or during the talk. I have a couple of backup slides for that. But to get started, so I'm currently an assistant professor in the Department of Computer Science and at the Atlas Institute at the University of Colorado in Boulder. And I started there in 2018. And as said before that, I was a PhD student at MIT. And a lot of my work was inspired kind of by what we see on this slide here. So this idea of could computation be more than us sitting in front of flat screens and typing away on a keyboard? And I'd like to invite you to just let this image sink in for a little bit and just see everything that's happening here, right? There's a child learning pottery, but there's material that changes over time. There's a really intimate connection between the teacher and the student in this case, so maybe the parents guiding the hands. The material changes over time. So this is a really deep, interesting, visceral experience that is happening here. And of course, a lot of that, as we grow older and as we grow more distant, gets replaced by something that we're experiencing right now, right? So we're sitting in front of computers and we're trying to exchange ideas, which works fairly well. I mean, computers are great tools, but still, if you were to paraphrase what Malcolm McCullough said in his wonderful book, Abstracting Craft, the eyes are in charge and the hands are underemployed when it comes to computing. So the question is, how could we bring the hands and the body back into computing, and especially in times like these where we really yearn for a more personal connection. And I don't know about you, but I'm literally stuck in front of a video screen all day long, and it's dragging me down. So what interfaces could we build to improve that? And so my personal inspiration, I think I saw Hiroshi in the audience earlier. So my professor Hiroshi Ishii is actually joining here as well. But this was my inspiration when I was an undergraduate student back in Austria in 2004. I saw this in a museum. The project is called SANDSCAPE. For those who have their video on, I see a few of you. Who has seen SANDSCAPE? It's been at the Boston Museum of Science and at the Media Lab. But just for those who haven't seen it yet, and to understand why I was so blown away when I saw it as an undergrad myself. It's an interface for landscape architects. So you have a sandbox, then you have a depth sensing camera mounted above this sandbox, and you can modify a 3D model. Here you actually see Hiroshi interfacing with this sandbox. So he's moving the sand around. The system senses the 3D geometry and then projects information back onto the sand. And back then, this was still an expensive system. Now you can actually get a lot of open source versions. They're used for geoscience. One of my colleagues at CU Boulder is actually doing wonderful classes using an open source version of this sandbox to teach geology students about plate tectonics, but you could also think about a lot of different applications when it comes to geospatial contexts. To me, what was really interesting though was not so much this individual application. It was more of the visual experience that I could have a computer that I dig through and really like kind of immerse myself in. And even though these are just static beads, it kind of feels like, you know, you're touching bits, so to speak. And I think that's where the kind of term tangible bits that was coined by Hiroshi comes from. So when we think about collaboration here, we see, you know, there's the interpersonal collaboration in terms of, you know, these two people and their faces, so talking heads. Then we have the hands, and then we have the objects that they manipulate. We've got a lot of fairly sophisticated tools. We're using one right now to transmit faces. It's still nowhere near as where it should be in terms of gaze and other expressiveness, but you know, it's about as good. In terms of shared objects, though, we've really much focused on you know, text-based documents, Google Docs, and in terms of our expressiveness, we're completely lacking the haptic sense communication channel of touch. So we were thinking about when I joined the group as a graduate student, we were thinking about how could we make a tool like this that has digital properties when it comes to representing the objects and the hands, because in this system here, you know, you can sense how you interface with the sand, and you can output you know, painted bits, so projection mapping on top of it, but you can't really computationally change the material. You can't really represent the hands computationally easily. You could only project on top. So we were like, what we really want to do is give this box of sand digital properties. And that was the starting point of my own research journey. So this inspiration has been around for a while, this vision. Ivan Sutherland, himself a PhD student, and you know, probably everybody here knows Ivan Sutherland and his work, but you know, inventor of the graphical user interface, later of the first virtual reality head-mounted display. We just celebrated the 50th anniversary of at SIGGRAPH in 2018. It's a wonderful panel, but he was talking about in this really great paper, The Ultimate Display. What would the ultimate display be? You know, if you're the person who invented the graphical user interface, what's next? And he was saying the ultimate display would be a room where the computer can control the existence of matter. So a chair displayed in this room would be good enough to sit in. Handcuffs would be confining. A bullet would be fatal. So it would be literally the wonderland into which Alice walked. And I find this highly inspiring, again, because it's so visceral. It's exciting, it's dangerous, and it's what we should build, ultimately. So, and we have a lot of inspiration for that as well. I mean, back in the day, movies like X-Men were showing these like tabletops that could shapeshift. We see literally like Black Panther, all of them, like every kind of sci-fi movie has some version of like physical programmable matter display. And so we were wondering, or I was wondering, how could I build something that is a table like that we can program? I looked a lot at these things like pin toys, where you can put your hand in, nails stick out on the other end, and said that would be a feasible approach that we could build. So that's what led to my first project called Relief, just trying to build like a motorized pin toy, so to speak, in the form of a table. And there's been a lot of previous work, especially in mechanical engineering, on building these. They're used for pin tooling. So this idea of you make a programmable mold because you want to form, for instance, springs of wagon carts. So this is the oldest patent I could find from 1863, where you could actually have a reprogrammable by a person mold for forming these springs. But and it's not a big jump to say, okay, we'll use motors and computers to do that. There's been a great project at MIT by Professor Hart together with Boeing on making these programmable pin tooling devices. It's a big project, I think, in the late 80s, early 90s. The question, and then in terms of computer interfaces, there were also these things called shape displays. So the idea, Sinotron, for instance, made one for Northrop Grumman for like military applications. So this idea of just like X-Men, you stand around the table, you can plan your next, I don't know, war-like scenario. But there's been a couple of different technologies on using hydraulics, pneumatics, combinations of servo motors, shape memory alloys to make these shape displays. The problem, of course, in my case, was my background was in software engineering and not so much in mechanical engineering. So I really want to say I tremendously benefited that around the time I built this open source tools in terms of hardware really took off. So I found, I by chance found a surplus lot of these motorized mixing board faders on eBay and bought them on a whim. They were very cheap, 150 of them. And said, with these faders, they would make great linear actuators. That's what they're meant for. So they're like, on your audio, what do you call it, mixing board usually. You press the button for a preset and they fly to where you need them. I said, I just wanna emphasize that without having Arduino and a really supportive open source community, both at MIT and outside, it wouldn't have been possible for me to actually start making a table like that. So I built out of these 150 faders with Arduinos, built my own little servos, connected them all over I2Cs with dozens of Arduinos that were then connected to a computer. And that's what you see on the right here, my first shape display, so to speak. So not that complicated to build, just tedious, but not complicated. And also fairly easy to replicate, actually. And again, that was really a mix of just open source electronics and fabrication tools. So the fact that we had a shop bot, had simple fabrication tools at the Media Lab that would make it easy for somebody like me to build something like that. And that's led to a whole series throughout my PhD of building different shape displays, so a whole range of them. And it's also built me to my current research career in guiding students on building the subsequent versions of shape displays. So I just want to give a big shout out. There were lots and lots of people involved in this, especially my advisor, Professor Roshishi, my very close collaborator, Sean Fulmer, and Alex Olwell, who you kind of see the lines here. I've worked over with on many projects, so don't see that as my presentation. See these as theirs as well. And then my current collaborators and students at University of Colorado, so Ryo Suzuki, who just graduated. I built a lot of the projects I'm showing with him. Clement Sang, who's also just graduated. He's going to be a professor at NUS in Singapore. And then my dear colleagues, Mark Gross, Ellen Doe, and too many to name, so I kind of ran out. But, and Mark also having a great connection to the Boston Chi scene. He grew up just outside of Boston and got his degree in the architecture machine group. That was his PhD before he went on to be a professor, and is now leading the Atlas department. I'm a professor at CU. So, so just to show you, and please do the videos work fine. Just a quick heads up to talk. The frame rate is okay in terms of transmitting. I don't hear any complaints.
It's slow, but it's okay.
Okay, good. Just let me know if it starts to stutter and make a restart. So you can really see this was the first shape display we built, Relief, and the idea here was very much related to SANDSCAPE, the interface that you saw earlier. So here we have Google Maps, we have a geospatial interface, and we can browse mountains. We can use our gestures to do so, so we can zoom in on a landscape. And if we have two of these tables, we can connect them and show somebody else a mountain and say, make spatial references to that. Of course, the resolution of this first shape display was really low. So we put a spandex fabric on top and projected models on top of it. But one very big kind of breakthrough for this project was that at that time, Microsoft had just come out with the Kinect for the Xbox, so the depth sensing camera. That really made a very big difference for a lot of our projects. And there was a very active open source community who immediately, wrote libraries for it so we could use it outside of the Xbox. So we started, my colleagues and I started investigating not only how could we display models, but also how could we interact with a shape display like that. So what you see here is a very simple, very simple CAD program. So this idea, go back to the first slide that I showed of clay. We were saying, could we use something like this as digital clay? So we can go use our hands, directly deform it. Again, if we had a connected shape display, that form that I create, in this case, very simple, I can only press in, but that form that I create immediately shows up on the other hand. I can feel it deforming. And we were also saying, it shouldn't just be clay, it should be more than that, right? Because we're using computation here. So we were also looking at what high-level commands could be issued. So selecting something, extruding a shape, scaling it, rotating it, just making like kind of your standard kind of transformations that you would do on a shape. And for a lot of those, there's no, when you make pottery, there's not really a command. So we were also mixing, using the Kinect, mixing the idea of can we use gestures for high-level commands? So you kind of see this pinch gesture where you form invisible strings and then you kind of puppeteer the interface and say now stretch or compress the shape. And then we have these direct gestures where I go in and directly deform. And the main problem or the main drawback, we started showing these at SIGGRAPH and so on, got very nice kind of feedback from the community. But our problem was that the resolution was just so low that there was no practicality to it. So that's when I started collaborating with Sean Palmer, my very dear friend and also a PhD student at the Media Lab at the time. And we just started making these mock-ups. So we're saying, okay, instead of 150, what if we had 1,500 pins? So what you see here, the stop motion animation, I'm just going to replay it again, was again for CAD, where we were just laser cutting 1,500 pins and making a little static prop that we could use for stop motion to kind of show what you could do with a higher resolution. So here we have a pin spacing that is 1/2 inch instead of 1.5 inches. The problem with these, it's always quadratics, hard to scale, but it still already shows in a modeling scenario we can do a ship hull. In this case, we've been sailing together on the Charles ship hull, we say. And so we went to our advisor, said, give us enough money to build this, and he made it happen, not for 1500, but at least for 900 pins. And that led us to this version here. That's been the most known shape display and also the most popular platform for us to actually work on these kind of telepresence experiments, and I'll talk about a little bit. So this display here called Inform is 30 by 30 pins, spaced half an inch apart, and they can extend 10 centimeters, what's that, 4.5 inches or something like that, from the table surface. And now here you can kind of see this original vision that we had come to life, where we're saying we want to have a space where we can program both contents, so we can display 3D models, we can deform them, and people's gestures and hands, and we can do so freely. So rather than having the standard approach to teleoperation, where you would have, you know, a robotic hand effector that usually mimics a human hand with 5 fingers or 2 hands with 10, and then you try and pinch things and move them around and grasp them. Here we have a freely programmable display that can display hands, but can also mix it by rendering data, rendering other sources. It's not limited, it's kind of agnostic to content. And this idea of like rendering people's body parts and transmitting information over that really kind of came by accident for us. It was kind of from debugging, you know, the first gestures that we had, you know, using this gestural interaction for RECOMPOSE, the project I showed before, and kind of just debugging, showing the Kinect output, you know, that depth image, and rendering that on the table to see if it works. And so this is really kind of us discovering that we could not only use it for debugging, but also just for transmitting shapes. Again, here you just kind of see a medley of applications that we were doing back then. So here, for instance, again, it's this clay-like modeling where we extrude a shape. We can start modifying it, or we can start, you know, painting on top of models. So here we have like our little Volkswagen Beetle that we're painting on, or moving data sources onto it. And if any of those grasp your interest, you know, just let me know. We can talk more about specific applications. We were really kind of running through a wide variety here. This one, for instance, is for showing mathematical equations, so rendering the formula you see at the bottom, physically at the top. So that means you can start exploring things like differential equations, see where's a local maxima or a local minima when you start rolling a sphere down. And here you kind of see the table we built, still sitting in the media lab if you have a chance to go there and try it out. So it's just 900 motors built into a table surface, and then mechanically linked to the tabletop. So it's a pretty big contraption, and I'm going to talk about, you know, what we're currently thinking and doing to kind of try and change some of that. So this idea of could we use this for remote togetherness? As said, kind of came by accident. We really started just playing with debugging, you know, Kinect data and transmitting that. So we're like, what if we, you know, here we're showing a 3D model of the plane, and we're like, what if we just take that raw depth input that we get from the Kinect and the RGB values that the color camera gives us, and transmit those? Can we now like accurately kind of reference things? Can we not only do that, but also move things, so physically interact with objects that are on top? If we had 2 of these, could we use them kind of like a membrane? So here you see 2 connected displays where I press into one end and the shape appears on the other, so we can press against each other, kind of have a haptic link to each other, where it kind of feels like we're connected through a membrane. So these were kind of the very first and fairly straightforward experiments of what you would think of. You know, you say, okay, I have depth here, and then I transmit that, and I just physically render depth over there. But for us, what became really interesting was this idea of, this is a programmable display. You know, that's kind of the very big advantage to, as said, your standard telepresence robot, where you can't really change the shape and where you can't really program individual pixels. So could we go beyond physically being there? We have, you know, our input space, we capture that input, then we compute, and then we output, and we project, and we render the shape. But that compute could change, you know. If we talk about computer graphics, we could just throw standard transformations on top of that. And so we started playing a lot with this idea. What if we could have, for instance, instead of just two hands, could we have three? Could we just render an extra one and copy things? Or here you're inspired by art and science fiction. Instead of like 10 fingers, what if I had 30? And so we started playing a lot with this idea of altering the shape. I mean, here, this is a very simplest experiment where we're like, okay, let's just selectively switch on and off shapes, but also switch on and off parts of shapes. What if I only want to render my hand, but I don't want to render my arm? Or switch on and off things because, you know, I have an object on top, so maybe I want to modify the object, pick it up, and turn on my shape, otherwise I turn off. Or start playing with transformations where I start to scale my hands. When I have like tiny hands to be more precise, or ginormous hands to pick up something large. In this case, just do a simple mirror transformation. So if I move towards the center, I can always capture the shape. Here I'm doing copies of my hand, so you can like leave a static copy behind to enclose this object that I wanna interact with. We especially had fun just because I ran through that very quickly. A lot of fun with this idea of like these geometric transformations. So here you kind of see my hands are too small to pick up this ball. It's kind of awkward, so I just start scaling them. And now with my ginormous hands, I can like comfortably interact with it, even with a single one. And this idea of beyond being there, I think that's to me the most interesting one, because right now so many of the tools that we have. And I mean, I'm talking about a very, very rich research history in CSCW. Beyond being, there's definitely a concept that we first stumbled upon. But for me, this is really the direction that's most exciting in using these shape displays. This idea of, okay, I could just try and be there in the same room and have as much presence as possible. But what if I could take the most appropriate shape for interacting with you. So here, for instance, we switched out all of the hands for different, end effectors. So instead of a hand, you have a scooper or a ramp, or chopsticks, or a parrot hook to grasp objects. Here again, I'm interacting with Sean here right now. He's soldering something and I'm bothering him, but I'm also helping him by like propping up the tool with one hand, leaving that as a copy, and showing him where he should interact. And though you see the resolution is extremely low, there's still something to that unfiltered kind of responsiveness that still lets us interpret that there is a gesture and there's a hand. We also experimented a lot with this idea of shared objects, and I'm going to go back to that a little bit more because that inspired a lot of our subsequent work. So this idea of rather than only rendering a shape through the deformation, we could also use the shape that we're rendering to interact with objects. And we can do so, either by scooping them up remotely, kind of as you've already seen in a couple of videos, or programmatically by kind of having the shape display sense where objects are and then try and move them, which is what's happening here. So I'm rendering the shape of the remote hand. There at the end, the pin popped off, and we're trying to fix it. That's kind of funny. We're rendering the shape of the hand remotely, but then we have two connected objects that the computer's tracking and that trying to move into the correct location. So for us, this idea of could we computationally interact with objects on top became really interesting, just because there are so many limitations to shape displays, right? And these limitations are pretty obvious. You know, it's not a full 3D shape that you can render. It's only 2.5D, so you can't go up. You can render depth, but you can't really have more complex objects. So my colleague Philip Schössler, during his master's at the Media Lab, worked on this project Kinetic Blocks, where he was saying, could we very precisely programmatically interact with objects on top? So if you think about, say swarm robots, you know, the traditional approaches, you have quite sophisticated robots that can connect to each other and then move, but it's very hard to build these robots, it's hard to power them. There's a lot of limitations if you want to use them for shape generation. What if these blocks were super simple and you have a more complex apparatus underneath to modify them? So using the shape display in order to stack blocks on top of each other. And there were some really interesting things of like, how could we propel blocks so they actually land on top of each other to make shapes? And how could we use, again, to the theme of remote togetherness. So here we have a simple experiment, kind of Lego-like. We're making a structure on one end with static blocks, and on a connected shape display over a distance, the computer tries and mimics that and tries and generates the same shape. So for me, this is something like, say, my own daughter, right now, a little over a year old, you can literally spend on Zoom, you can have her for like 1 minute with her grandparents who are back in Austria, but it doesn't really matter, I don't really would be, because you can't meet her, right? So after a minute, she first waves and so on, but she can't really have a meaningful interaction with them. And she kind of starts freaking out. So stuff like banging the keyboard and so on, she gets bored, right? So this idea of could we do something like connected play over a distance where they make a structure and she can actually sense that and interact with that, because she's pretty good at playing with blocks already. Quite proud of that. So here you kind of see, there's a structure that the computer can modify to this shape display. So I can select and again, to me, like this idea of remoteness, of saying, can we physically transmit gestures? Can we physically transmit physical shapes? And then can we interact with those directly? Are amongst the most powerful, ideas that we explored. So these shapes are still pretty low fidelity, but they're quite expressive. You can do a lot of things here. Beyond these like simple blocks that you saw earlier, there were actually a whole range of active blocks. So this idea, could we make blocks that have other outputs, where you translate the pins to rotate, and these connected blocks that have embedded magnets, so they can actually attach to each other and build more complex structures. So this idea of connected blocks is what I took further with my collaborators and my PhD student, Ryo Suzuki. Here we started making a shape display where we're saying, could we use it to use thousands of blocks on top? So if I had a super fast 3D printer here, and you had a very fast 3D printer over at your place, it doesn't take hours to build a shape, but it takes minutes or seconds, that could really help us collaborate with each other. So here we have a shape display that has 3,000 blocks that are embedded, and then the pins start pushing up these shapes and start kind of like work as a massively parallel digital 3D printer. And again, all these blocks, they have like Lego-like connectors at top and bottom, and then they have spherical magnets embedded at the edges, so they can connect side to side as well. And while they're in the shape display, those spherical magnets, we can have separators between them, and then we can start disconnecting them as we push them out to programmatically make shapes. And then when you want to make your next shape, so those are less interactive, of course, than those earlier ones we saw, but they're higher resolution, which is pretty exciting. And if we want to recycle those blocks, we kind of just push them back into the shape display, start making the next one. So this interaction, I mean, if you're interested in any technical details to that, we published this in 2018, but I'm more than happy to go into more details. But on the other hand, so this was one experiment of could we change the expressiveness where we not just start pushing in and out or start only having disembodied gestures that are picked up by Kinect, but can we actually have objects that give us a rich interaction that because the interesting part is here we have a 3D printed object, but we have a 3D printed object that I as a user later on can also modify and change, just like I can change Lego blocks. So the interaction becomes a more interesting one. And because the assembly happens from bottom up, it can also even interact with the assembly of the object while it's being printed. So that's really exciting as well in terms of human-computer interaction. So we'll move forward. And one idea that always interested me was, these are pretty big objects, these shape displays. You can kind of see that they're like not something you would have in your pocket, they're more like a tabletop. So we're like, what if rather than just being a tabletop, because most people that I interact with that see these videos, they're like, oh, they're fun, but could you just make a phone that does that? And I'm like, no, I can't. And that's kind of the end of the discussion. But of course we could shape these, and there's really interesting ways to do that. But I was more interested in going the other direction. Could we scale them up? And so we looked at, could we make a whole room that is a shape display and interact through that? So this project LiftTiles is exploring that. Again, my PhD student Ryo Suzuki, but then also our collaborators at University of Tokyo and Kyoto University, Professor Kaki, Professor Nakayama. So this is a very collaborative effort. So this project LiftTiles, we started making these tiles. We were like, what if we make a room-sized shape display? Our main problem was, we had so much space that we kind of wasted, that we had to use underneath to put our actuators into our linear motors that will push up pins. So could we make really, really compact pins that we can kind of use like tiles? So we lay them out, these flat tiles, these base plates, 20 by 20 centimeters. We lay them out, they're fairly flat, and inside they have a pneumatic tube that expands when we connect it to an air compressor. And then we use solenoid valves to control height, in plates and two plates. So we can start laying out these tiles, we connect them, and then we have a room-sized shape display. And we can also do that on walls. So you can see in the video, we have both floor and wall tiles that we're playing with. But really, the basic principle of these is, they function kind of like party horns. You blow in, they have a constant force spring that unrolls and creates a large displacement. And just one quick example. So we did think mostly about reconfigurable environments at first. So this idea, could architects use these to make pop-up structures? So could we have a shape display? There is a workspace in one moment, and then in the next moment transforms into a living space. But also this idea, could we use them for, say, for instance, for virtual reality, room-size virtual reality, where we get very low fidelity, low resolution haptic feedback. So wherever I have a low resolution object rendered in VR, I can feel a block in real reality. And again, those could come in from the walls, they could come in from the floor. Quite low resolution and not very fast, but fascinating in terms of how it feels when you see an object in VR, and you can actually feel a rough approximation of it in the physical world. And again, for me, we didn't run any remote experiments with that, but that would be, to me, one of the most interesting ways of trying out, could we connect two spaces with each other, where I can actually modify a block and you can feel a block over there, in order to feel more presence, in order to interact with each other in a playful or creative manner. The other one, so of course, the shape displays that you've seen so far, they were usually quadratic layouts, but then we looked at, could we use, rather than having, you know, one big bulky kind of machine, could we have a lot of simple, small, tiny machines that then come together to form a shape display whenever we need it? So this is a project called ShapeBots, and ShapeBots is a shape-changing swarm robot. So the idea being that they're kind of a shape display on wheels. So we have these little robots. They're based on little wireless Arduinos, wheeled robots. They're tracked from below on this tabletop surface. You can move them around, and we call it a swarm. But so it's 10 robots here. I think was the maximum that we ran at the time. And these robots move around and they can change shape. And so then we looked at, you know, could they come together if we want to like render a low resolution shape, but what degrees of freedom could we have in order to make these more expressive shape changes happen? So here you, for instance, see a data visualization where we're looking at population data across the US, and I can move this around and I kind of see a physical bar chart of population. Or again, we're really fascinated by this idea of how could these shape displays actually interact with the physical world. So here, you know, they're cleaning up the table for you, so they're moving around, or they're adding physical affordances to objects that usually don't have them per se, so digital affordances. Here, for instance, they're surrounding a coffee cup, the coffee spot, so they're putting up a physical barrier so I don't burn myself absent-mindedly. And then as it cools down and gets ready for consumption, they kind of lower that barrier again and move away. So you see a lot of these experiments, you know, are whimsical, but I think absolutely realistic in terms of how we could see them play out in our daily lives. I absolutely think that you know, I have a swarm of these robots sitting on my table. You have one sitting on yours, and you're able to transmit even the slightest gesture towards me, but you have physical presence in the same room with me, which is so much different from having just pixels floating around on a computer screen. So if I could have a representation of even just, you know, an audience of 10 on my table next to me giving this presentation, seeing if somebody raises a hand, to me that's so much different from seeing maybe a, you know, an icon on a little side screen here. So these ShapeBots, and there's a couple of technical innovations in here that I could go into detail if you're interested, especially these actuators that move in and out, kind of inspired by tape measures. So they're very compact real actuators that we can control to change the shape of these robots. And that really is what turns them into the mobile shape display. And then there's a couple of details that are fairly straightforward on how we track these robots, how we control them. But an interesting part is really, for us, an interesting insight was this idea of, you know, finding kind of a middle ground between, you know, we can have very, very simple swarm robots. So here we ran some simulations of, you know, what data can we represent with 30, 40, 50 robots that come together to render a shape, or we could have like slightly more complicated swarm robots that can not only move around and assemble into a shape, but also change their own shape just a little bit, you know, move in and out. And we can actually get a lot more expressivity out of that because we have more degrees of freedom of what we can show. And we started combining these ideas of could we have a room scale shape display that also can change shape? So that kind of brought us to this last project that I'm going to show called Room Shift. So we just showed that at Kai this year, and this idea behind Room Shift really is if we have a swarm of shape-changing robots, could we use those again to affect physical props in the room that we use to assemble shapes? So those could be existing props, like for instance this chair here, that we can lift up and move around, or they could also be props that we custom make to assemble. So for instance, these wall elements that you see in the background there that move around to represent the shape. So what we're doing here with the swarm of robots is encounter type haptics. And what that means is, as I am in virtual reality, if I see a chair, you know, I want to be able to sit in it. If I see a desk, I want to be able to lean against it. If I see a wall, I want to be able to touch it. With the past shape display, like say LiftTiles, we can't really, you know, realistically render these objects at a high enough resolution. So what if we instead use a swarm of robots that we can control to move around these props and to track the person moving through the room and move the props into place just as they use them and just as they interact with them. So that makes virtual reality more engaging because I can now start, you know, being in a scene, teleporting around in the scene, and as long as the robots are fast enough and close by enough, they can start assembling the scene around me so that if I see a prop, I can actually interact with it. And we're talking mostly about, you know, simple room scale props. We kind of like built a little taxonomy of what would you usually encounter, things like tables, chairs, walls in an office. And again, for me, the really interesting part that we haven't gone to at this point would be how could we actually use this to really help remote collaborations? So could we have something where, say, I'm an architect with clients, as I change a room layout and they experience that in a remote place, you know, they can actually not only see but really experience it from different viewpoints. They can sit down and see, would I like this? Would I like this layout? Does this layout make sense for me in terms of like ergonomics, for instance, which are really something that you can only start testing when you actually interact with the physical objects. And if you say that's unrealistic in terms of complexity, I don't necessarily think so. I mean, there's a lot of pieces of, you know, that are still missing. But say if we take the ShapeBot robot, ShapeBots robots that you saw earlier on the tabletop, we're talking about like material cost of, you know, less than $30 per robot. If we talk about these room shift robots, you know, we actually just went out and bought Roombas. iRobot is kind enough to have a very open, accessible port, and there's great Arduino projects that easily let you program those. So that's what we did. And then we added these target laundry racks to make these scissor lifts to pick up furniture. And so the cost per robot is actually also surprisingly low, and we're talking about like, you know, hundreds of dollars. So you can easily build a swarm of 10 of them, and they're not too expensive actually, especially compared to all the time and money we're spending right now being stuck only to our screens. So that kind of brings me to a last kind of what's next section, and that's really more of like where do I see the most important developments to make these accessible. For us, a really important one was just taking these ideas that are out in the robotics community and especially in Boston. It's kind of like the cutting edge of soft and swarm robots. So we just got inspired being in this environment and now being intellectually connected to it. But the idea of, can we use soft inflatables to make large-scale actuators? Can we use swarms that assemble in order to render shapes? Can we use new materials that come out of soft robotics? So here's an example in terms of fabrication methods and actuators. This is a project, the very first one you see by the Keplinger group that is now headed by Professor Christoph Keplinger at the University of Colorado. And they developed a new type of high voltage electroactive actuator that is called Hazel, and a very easy to implement fabrication tool chain, so where you can heat seal these actuators out of simple deformable plastics, fill them with oil, add electrodes, and have a muscle-like performance. So there's still a lot of questions to be answered, and like, for instance, they require very high voltages to actuate. But I'm just saying, we're really inspired by the soft robotics community, and I think there's going to be a ton of innovation that is going to seep over into HCI that we can benefit from. So we're currently doing a collaboration with the Keplinger group on these topics. And that's just one kind of point example. To me, it's really like kind of an idea of where do we want to go as a community and as an industry. It's so hard for me making an ultrasonic wave motor right now, even though those would be great for a linear actuator. On the other hand, Canon and Nikon, makes, I don't know how many hundreds of thousands or millions of those for all their lenses. And they're cheap and they're reliable and they work really well. It's only really kind of where do you put the effort in terms of your fabrication power, and how do you give that access to the research community? Apart from that, I really think a lot of the tools that we developed and the applications and interactions, like the examples that I showed for remote collaboration, really only came because we had a shape display. We didn't think of them out of thin air. And so to me, that's a really interesting research topic right now that we're working on. So this idea of, could we have prototyping tools that allow us to build applications without having a shape display? Because we have a lot of other amazing tools at our disposal now. And one of them being, spatial sensing and immersive spatial graphics. So just the idea that now we can reliably track people and objects in an environment, and we can have great immersive graphics, and which we didn't have even a few years ago. And now we can connect those to simple robotics in order and not even necessarily robotics. I can start prototyping things with props just around my house, and we've started doing a lot of that. Here in the center, you see one of my students, Mel Platt, who's doing a master's. We started working on a shape-changing kind of robot prototyping platform, and she's cutting up Amazon boxes, which we have lots of these days in our house, and using those as a prototype material to experiment with how we could mimic shape change. So I really think these kind of very, very simple toolkits could really have a tremendous impact in exploring the application space and also kind of broadening our mindsets. And that kind of leads me to conclude. I think we're at about 1 hour now. So I'm just to reiterate, I'm currently a professor at CU Boulder at the Atlas Institute. So that's our campus right now. I'm not on campus. We're still in lockdown, but also I'm physically located in New York. Kind of got stuck here on parental leave during the current situation. But that kind of led us to say also, could we really push these ideas of connecting spaces through immersive graphics and through robotics, and kind of start making these labs connected to portals. So I actually started a lab here in New York now, where I'm currently based, called Atlas NYC. So that's kind of a satellite lab, and we started collaborating with universities here. I'm on the East Coast now. We're just working with an incredible group of students at Columbia University to build tools for remote togetherness that we're going to connect with Boulder. And then this fall, we're doing a course together with students at the new school, Parsons School of Design. So we really kind of wanna not only overcome kind of what we got thrown into through this current situation, but really like openly embrace it and say, you know, are there new things that can come out of it? I really like that in the, like looking at the shared whiteboard that we had before the talk, this idea of like what came out of it. I mean, this is the world's in a bad place, of course, right now. But then on the other hand, there were so many things that were, you know, that we knew beforehand in terms of like unsustainable travel. It was a huge topic last year at WIST. You know, there was a keynote on like how could we actually, as a HCI community, go forward and build new tools that allow us to be both more connected and more sustainable at the same time. And now we're kind of forced to think about it every day. So that might be like a small kind of uplift in all the madness that is going on. And I'll end my talk with that. Reach out to me if you have any further questions, and I think we'll open it to questions. Thank you so much.
Yeah, fantastic. Thank you, Daniel. We have a few questions here. One is, have you seen any public applications of shared displays outside of the lab or academia?
So we've done a couple ourselves. I've been always very kind of, how do you say, trying to push, because as I went back to the very first example, the only reason I got into this whole field of tangibles was because I saw SANDSCAPE in a museum myself as an undergrad. So for instance, the Inform Shape display, we put back into the same museum for 2 years back in Austria. So a lot of kids in the public could experience it. We also had it at the Cooper Hewitt Design Museum in New York for half a year, and it shows like Milan. I mean, those are at the Milano Salone, but those are really still like point samples, because the main problem is they're just so expensive and hard to maintain. So you know, you can do it for a museum. There's been a ton of examples in terms of using them for marketing, and so we've seen like building size shape displays at the Sochi Olympics, for instance. Asif Khan did one, which was a selfie booth. So, you know, you take a selfie with that camera and then you show it on a building scale, you know, this case growing out. Amazing engineering. But again, these are kind of like publicity stunts that in order to go viral. I think we're gonna see, just in terms of like cheap robotics, I think this like swarm robot approach is actually gonna allow us to push it out into schools. And I mean, of course, if you want to say a turtle robot, you know, is a shape display, that of course there's been lots of it, but you know, it's a very blurry line. So I don't know where one starts and where the other ends, but I definitely think we're gonna see these like cheap swarm robots that you know, are in the like low hundreds of dollars for a kit that could be pushed out, and that actually allows to render data and allows to connect people to each other. So because, and I don't want to like just pile on this point for too long, but I remember like when I joined the Media Lab, SANDSCAPE was like this great demo. It was around for a couple of years already. And the first version that they built was based on a Minolta laser scanner. That alone cost $50,000, I think was what I was told. I don't know the exact price. Projectors were incredibly expensive at that point still. So you know, late 90s, early 2000s. And so we were like, this is such a great project, but nobody's ever going to use this because, you know, you're talking about tens of thousands of dollars. How are you going to put that in schools? And now a few years later, you know, we have a Kinect, which you can get for $100. We have cheap LED projectors, which have a, you know, life of 50,000 hours. And you can literally, you have these in schools now. So, and I see undergrads at Boulder using them to understand geology better. So I definitely think that we'll see this. Hardware is hard, but it's possible. So.
Very excellent. Thank you. I have two quick questions. One, it seemed to me that ShapeBots have a little eyes and maybe a face.Maybe I'm anthropomorphizing, but is that something you did on purpose? Yeah,
it's great. It's really funny that you say that. So those are actually ports you can plug in through the mouth. That's the micro USB connector to charge them. And then one eye has an LED with a status light, and the other eye you can press the reset button. And I asked Rio, who's really the lead on this project. He built these from the ground up during his PhD, and he was really into the idea that they looked like a face. So yes, they're actually consciously. And I was always annoyed that they have like, you know, these wires dangling out at the back. Those are the connectors from the little ShapeBots to the linear actuators. But then Rio convinced me that they're just like hair, like kind of like dreadlocks hanging out in the back. So yes, there's a lot of anthropomorphizing. And I should keep my answers shorter, but so yes.
No problem. What have you been doing since Microsoft stopped producing the Kinect?
So for one, you can still get the Kinect. I mean, Microsoft has now released the Kinect Azure, so their newest one, which is much more powerful. So they're actually, in that sense, it's pretty great. There's been a continuing stream of amazing depth sensing cameras. It's kind of complicated because you are at the mercy of you know, like say after SANDSCAPE, my very first job actually as a grad student was to buy a time of flight camera, because those were cheap at that point before the Kinect, and make a cheaper version of SANDSCAPE with a time of flight camera. And so that was the like C-Cam, I think. It was like $1,500. And then that got bought and put off the market by Microsoft, actually. And so we were like, oh, what's happening here? And then they released the Kinect. So you're kind of at the mercy, because obviously, you know, you can't build your own time of flight camera, and you can only build them cheaply at scale. But I think in terms of sensing, we're seeing so much right now. Like I just bought the newest iPad, which has a, you know, LiDAR built in. I mean, the iPhones had it front facing for a while, but now, you know, they actually have it for room mapping, and it works pretty amazingly. So I'm not that worried about like hardware. But yes, there is always this constant struggle, and I really think, I mean, it's you have to have a powerful, emboldened open source community that like takes these things the moment they get on the market and like starts making open source drivers for them. I think that's and I think companies have really started to embrace that also. At least that's something that I'm seeing now. That's great.
Yeah. The next question is, do you have any insights or suggestions on how to best support remote control or collaboration on tasks that require more fine-grained control, maybe like assembling Legos or wiring circuits?
Yeah, I mean, I have some ideas. I don't think that any of the tools that I've shown here would be sufficient to do anything fine-grained, even if you were to scale them in terms of you know, precision and resolution. There's still like fundamental limitations of what you can do with an approach of, say, for instance, these pin displays moving up and down, or just linear actuators extending off a swarm robot. But what I do think, where it's really powerful when we talk about remote collaboration, I think a really interesting aspect would be that the idea is that there's humans on both ends, and humans are amazing in terms of fine-grained control. So rather than, you know, the robot having to do everything, I could use the robots to kind of like make a gesture or nudge the human into the right direction, and then to give instructions. And I mean, if we've seen a lot of like haptic instructions over a distance using gloves. I've personally never been a huge fan of them myself, just because all the ones that I've tried, you know, were like too rough in terms of the feedback they would give me, and you know, would require this, like, you know, they kind of have to strap on everything. And so I always felt like, you know, I wanted to have something that is less encumbered. But that's also, I haven't really seen, like, you know, I haven't tried like the haptics gloves, for instance, which through microfluidics have very high resolution tactiles at the fingertips. From the videos that I've seen, I haven't tried them. So I'm very easy to convert when it comes to that. But I really think, the powerful tool would be to say, use the robot in this case for rough tasks, for more like gestures, sketches, moving things roughly, and then in order to help me as a human on the other end, like to inform me. And I think there's a lot of powerful interactions that we could explore in that sense. And that might be because everything else that you want to do that is precise that I've seen in robotics, like in teleoperation, usually means you just have to slow down a lot, and then you lose the human component. So you do something in 10 minutes rather than 10 seconds, and then it loses interactivity.
How much of your research has involved the general public, and what are their reactions to these sorts of technologies?
So it's kind of a double-edged sword, because so Inform, the project that I showed, you know, halfway through, that's become our most public project, and that's really been viewed. It's kind of funny because it was first a cell phone video, like a visiting professor. We hadn't published anything on it yet. We just showed like a rough interaction. And there was a professor visiting the media lab, putting that video online. Was fine, you know, nobody really cared that much until like somebody on YouTube like started putting it on YouTube, and then started putting it on Reddit. And on Reddit, the headline was something about like, you know, what was it? Something about, it was like some sexual innuendo on you know, the remote to get, and so immediately that like blew out of proportion. And on YouTube got millions of clicks right away, and we were like, what? We didn't even have anything to do with that. And so we started making our own video. That got a lot of traction as well. And it's kind of like going back and forth. So the problem that I have with these is you can make a nice video, but half the time, you know, we're talking about the importance of haptics and of touch and of, you know, having physicality, but everything I'm showing you right now is a video. Could all be rendered, right? So I think really involving the public will be, I mean, so far we've done it through outreach and through museums, but that's not enough. Like, we really gotta get these things out there into schools and into people's hands. I think it's possible.
Well, that'll be a wonderful day. One last question. For projects like this, how do you evaluate? It says, how would the evaluation often look like? I'm guessing, it's, how do you evaluate the success or failure of any technique?
I mean, there's a couple of different answers. Some of these projects we didn't really evaluate. We just said the novelty is good enough, and we just threw a technical evaluation at it, where we said, you know, can we reliably, you know, reproduce a certain performance of moving an object across. But I think, say for instance, the physical telepresence paper published at WIST on you know, moving objects with a shape display over a distance. So that we actually did an evaluation where we gave people a task on moving objects, because we were like, as I said, we just started playing around with, could we copy people's hands? And then we realized, oh, if there's an object and we left something on the table, and we're like, oh, we can actually reliably move this object through this new method. And then we started evaluating. It was a pretty small one in terms of sample size, but we got very good results that were statistically significant on how people operated and actually were able to complete the task. So that's one. But again, because the usability compared to, say, any other like groupware projects is so, and the reliability of these systems is so much lower, you know, you often have to see them as like physical sketches almost. You can do an evaluation, but it might not be as meaningful because the technology keeps changing.
Well, that's extremely reasonable. Well, that's all the questions tonight. I have to say this was an extremely interesting talk. So thank you very much, Daniel. We're super glad that you could join us tonight. And thank you everyone else for joining us as well. We'll be posting a video of this probably later this week, and Daniel will send you a link, and we'll also share the link out on social media. So thank you very much, everyone. Have a good evening.
Thank you so much.
Bye.
Bye.